Hi, I'm Anna.
Hello, I'm Melinda,
And I'm Xiaoyu.
and today we'll be talking about Chapter 28, Fundamentals of Circuits. First, we'll start off with Kirchhoff's laws and the basic circuit. So for Kirchhoff's law, total current in a junction is equal to the total current out of a junction. So whatever goes in also is the same amount as the current that goes out.
And for Kirchhoff's loop law, it says that because due to conservation of energy, the sum of all the voltage drops is going to be equal to zero. So if you go around in any given loop and add the voltage, it will be zero.
Alright, so circuit in series. When components are in series, they are pretty much aligned end to end, and they're with no nodes in between them. So the facts about circuits in series are that current will stay the same throughout all components. Voltages is equal to the sum of the individual voltage drops, and the equivalent resistance is equal to the sum of all the individual resistances. So our equivalent would be, for example, from the picture in A, two resistors in series, it would just be R1 plus R2. Alright, so as seen from that video, um, it shows starting from one light bulb and put into series with the second light bulb at the end. Um, the light bulbs are the same resistance, and the current and voltage drop are they're the same throughout both light bulbs. The equivalence resistance for the circuit in series would just be the sum of the two light bulbs with the extra resistors, which are both the extra resistors are both 380 ohms, and they're put into the demo to lower the brightness of the light bulbs. That's it.
So circuits in parallel. Components are said to be in parallel when they share two or more nodes, and the current for a circuit in parallel is going to be equal to the sum of all the individual branches. This is the same as Kirchhoff's junctions laws, and for the voltage for a circuit in parallel is going to be equal across all the components, and the resistance diminishes for a circuit in parallel, which we can see from the bottom right picture that the equivalent resistance is going to be equal to 1 over R plus 1 over the other resistances, and then you take the inverse of that, and that's how you would find the equivalent resistance.
Okay, so here I have the circuit that has three components in parallel. So you know that they are in parallel because they each share two nodes. So this light bulb shares two nodes with the battery, and same for this light bulb. They all share two nodes, therefore they're all in parallel. And in a circuit that is in parallel, or for any circuit, the total current is going to be equal to the sum of the individual branches. So if we close the circuit, you can see that the current in this wire splits into this wire and this wire. And so whatever current is going into this node here from this wire is going to be equal to the current that comes out of this wire plus the current that comes out of this wire. And because this circuit is in parallel, you can tell that these light bulbs both have equal brightness since they also have the same resistance. And also, because they are in parallel, that's also why the light bulbs are very bright, because when components are in parallel, the resistance is less, since here the resistance would be equal to 1 over 10 plus 1 over 10 it would be equal to the inverse of that, whereas if the light bulbs were in series, you would add the resistances. So the resistance is less, which is why the light bulbs are much brighter and they're equal brightnesses, again because the voltage is equal across all the components.
All right, now for energy and power. So a battery uses energy and not current. And for an ideal battery, the change in voltage of a battery is equal to epsilon, and the change in potential is minus the charge and epsilon. And the epsilon is the electromagnetic field of the battery. And so the power of the battery is equal to current times epsilon, which is in units of watts, which is also joules.
And the power dissipated by the resistor is given by the equation, which is the current multiplied by the change in voltage of the resistor, or the total voltage drop from the resistors, which is also equal to current squared times resistors, which is also equivalent to the change in voltage squared over resistors. So most of the power will be dissipated by the largest resistance. And we see that the power delivered by an EMF is equivalent to the power dissipated by resistor.
And I wanted to point out another thing about how most of the power will be dissipated by the largest resistance. So this can be seen on the right diagram that you see on the right. The light bulbs have more resistance than the wires, which is why more power goes through them. And that's why the bulbs are brighter than the wires and more hot than the wires as well. So for short circuiting, it occurs when there's very low resistance made between 2 points in a circuit. So this could be sometimes when there are two conductors in contact. So this short circuiting happens when the current is equal to epsilon divided by R, and R would be a very low or zero resistance. And so when you plug in this equation, you'll see that once zero is in the denominator, the current is pretty close to infinity. And that obviously cannot happen in the real world, which causes the short circuiting to happen. So here's a quick demo of short circuiting. What a short circuit would look like. So right here, I have an example of what a closed circuit would be. And so when it's a short circuit, it's when a connection of very low or zero resistance is made between 2 points in a circuit that are normally separated by a higher resistance. So in this, I have a 9-volt battery, and I also have a regular light bulb that has 12 ohms of resistance. Now, when there are very small resistances in a circuit, in Ohm's law, which states that E, which is a constant voltage, which is in this case the battery, 9 volts, is equal to I times R. And I is current and R is resistance. And so in Ohm's law, if resistance is really close to zero or is at zero, then the current increases, which makes the wires heat up and is the most frequent cause of electrical fires. Now, luckily, we have safety precautions such as fuse circuit breakdowns that blow or trip up the circuits to prevent the explosions from happening due to the electrical fires. But in this case, when I move the resistance of 12 ohms of this light bulb to zero, you can see that the battery starts to blow up. And this is because the current goes super high once R is equal to zero. So the current is pretty much reaching infinity. And this is what happens when a short circuit occurs. And thus the battery does not light up because it is shortening the circuit. So it does not reach the battery and it does not light it up.
Okay, and so ground. Whenever you're looking at circuit diagrams, they're usually going to have the ground symbol at the bottom, and ground is basically just a reference point from where you measure all your voltages, and so you always make the ground equal to 0 volts, and the purpose is mainly to help prevent incompatibilities when you're doing circuit analysis or just solving circuits.
And I believe that's it for chapter 28. Thank you for watching.